Continuing Chapter 7, we'll look further at the free cash flow model, as well as two other methods for valuing stock. Before moving to the other methods, we need to look at the free cash flow method a bit more. In this approach, we'll forecast sales, net operating profit after tax, NOPAT, and total operating capital as a percentage of sales. From the mini case, the company is considering the acquisition of Hatfield Medical Supplies. The data regarding Hatfield is shown on the slide. Sales, $2 million. Total net operating capital, $1,120,000. Operating profitability ratio, 4.5%. Capital requirement ratio, 56%. Targeted cost of money, 9%. Operating ratios are not expected to change, but sales is expected to grow at non-constant rates for the next 4 years before stabilizing at a 5% long-term growth rate. Here's all the given data in table form. This demonstrates the calculations for year 1 with sales growing at 10%. NOPAT is expected to remain at 4.5% of sales. Operating capital is expected to remain at 56% of sales. Given those numbers, free cash flow for any year is equal to NOPAT for that year minus the change in operating capital. Return on invested capital, ROIC, is equal to NOPAT divided by operating capital. This table recaps our forecast for Hatfield Medical. See in the notes, free cash flow is negative in year 1. ROIC is less than the 9% cost of money. Using our free cash flow non-constant growth model, we can substitute our numbers for Hatfield and find the horizon value at time 4 is $1,260.65, and the present value of their free cash flows is equal to $64.45. Taking the present value of the horizon value and adding the present value of the non-constant cash flows, we arrive at the value of operations for Hatfield, $958. Looking at the Hatfield Medical results, the ROIC of 8% is less than the targeted cost of capital of 9%. That means Hatfield is not earning enough to compensate investors. ROIC must be greater than the weighted average cost of capital divided by 1 plus the long-term growth rate for the horizon value to be greater than the total net operating capital. The key variables that drive free cash flow are sales growth, operating profitability, capital requirements, and the cost of capital. These are termed value drivers, and they're variables that management can influence to impact the intrinsic value of operations and the stock price. We'll look at the impact of changes in each of these on the following slides. First, what if sales grows at a higher rate? As the slide shows, higher sales growth decreases the value of operations at time 0. The ROIC must be greater than the weighted average cost of capital divided by 1 plus the weighted average cost of capital for the growth to add value, and it doesn't. In this case, growth hurts value because the ROIC is too low. Higher operating profitability does increase the return on invested capital such that it is now greater than the adjusted cost of capital. So higher operating profitability does increase value. Lower capital requirements also increases return on invested capital so that it exceeds the adjusted weighted average cost of capital of 8.26%. Again, lower capital requirements increases value. What if we can increase operating profitability and lower capital requirements? The ROIC is much larger, increasing value. Finally, what if all 4 improvements are made? The ROIC is now higher than the adjusted cost of capital, and value is clearly increased. This chart summarizes our results. The slide recaps the conclusions. When ROIC is low, growth is not good. When growth is low, increasing ROIC is good. When ROIC is high, growth adds value. From our examples, we can see that small changes in return on invested capital, growth, or cost of money can drive large changes in value. The only thing that causes stock prices to move is news, new information that causes investors to reassess their estimates on growth and required return. This new information could be market-wide, such as a change in interest rates, or an overall change in investors' risk aversion, or it could be something company-specific that would change the expected growth rate. If stock prices don't move, then no news is entering the market. Closely related to the free cash flow model is the dividend growth model. Does this look familiar? Think back to our basic FCF model, but replace free cash flow with D and weighted average cost of capital with RS. You covered this in your undergrad finance class, and here it is again. Same formula, but now we're discounting dividends rather than free cash flow. This formula can value any stock, but the problem? The infinity sign. There's no closed form solution for this. In order to value stock, we have to make some assumptions about the dividend growth pattern. Note that the hat over the P indicates that it's an estimated or expected value. Actually, D1 and all the other Ds should also really have hats, since they're expected as well, but it would be messy. Conversely, T0 without a hat is the actual stock price right now, and D0 is the last dividend paid. RS is the required return on equity. Suppose dividends are expected to grow at a constant rate, G, forever. For a mature, stable firm, this is not a far-fetched assumption. The point of all of the above is in the last line. As T approaches infinity, the discounted value of D sub T approaches 0. Assuming a constant growth rate that is less than the required return on equity, through the use of a Taylor expansion, our general formula converges to the constant or Gordon growth model. Looks a lot like the free cash flow model, doesn't it? In this formula, D0 can be observed. It's historical. The required return on equity can be found using CAPM. If we know the constant growth rate, we can estimate the value of the stock. But what if the constant growth rate G is greater than the required return? You can't apply the constant growth model, as it would lead to an expected stock price equal to infinity. Not feasible. We saw the same situation with the free cash flow model, where the long-term growth rate cannot be greater than the weighted average cost of capital. Here's a simple example to recall Chapter 6. Given beta, the risk-free rate, and the expected return on the market, we can estimate a required return for the firm's equity. The missing piece for the constant growth model. Our required return, 13%. Given the last dividend of $2 and the growth rate and required return on equity, plugging into the constant growth model is easy. Our example stock is priced at $30.29. Note that the constant growth model is not applicable only to find the price of a stock at time 0. It can be used to find the price at any time in the future using the same data as for finding the price at T0. Even simpler, if you know the price at time 0 and the constant growth rate, then you can estimate any price in the future, since the stock price grows at the same rate as the dividend. 30.29 times 1.06 is 32.10. Dividend yield is as shown on the slide. The next dividend, D1, divided by the current price. Price appreciation is just the change in price. New price minus old price divided by old price. The return on any investment is made up of two parts: cash return, dividends, and price appreciation or capital gains. The sum of the two has to add up to required return. The sum of this two has to be 13%, and it is. We've looked at using the constant dividend growth model to value a share of stock. In truth, we can observe the price of a share at any time. What we can't observe is the required return, and that's the variable we need as a component of a firm's overall cost of capital. We can find the implied required return by solving the constant growth model for R. Note that the resulting equation divides the required return into its two component parts, dividend yield and capital gains yield. So what do we do if the dividend growth rate isn't constant, or it's greater than R? If we can assume that at some point in the future it will be constant, we can combine the methods we've used to value a non-constant growth stock. This is basically the same procedure we followed with non-constant free cash flow growth, but we're applying it to dividends. Step 1, estimate the dividends for the non-constant periods. Step 2, use the first constant growth dividend to compute the horizon value, or the value of the stock at the end of the last non-constant year. Step 3, discount each non-constant dividend back to time 0. Step 4, discount the horizon value back to time 0. Step 5, sum the discounted values. Hearing this method in words is a bit confusing. I suggest you focus on the chart on this slide. Pay particular attention to how the horizon value is computed, specifically which dividend is used. This seems to be where most errors occur. A slightly different version of the same chart is on the next slide. This version of the chart, mine actually, tries to highlight 2 points more clearly. Which dividend is used to find the horizon value? It's the first constant growth dividend. How far back the horizon value is discounted. In this example, you use D4 to find P3. So P3 and D3 are both discounted back 3 years. You can solve this problem using the cash flow worksheet in your calculator, but you really need to understand this chart in order to get the cash flows right. Taking the values from the previous slide, you can use the cash flow worksheet to find the value of a non-constant growth stock. Note that cash flow 3 is the sum of D3 and P3. This will also give you a chance to review the use of the cash flow worksheet, which we'll continue to use in later chapters. And the same method can be applied to free cash flow evaluation. Using the NPV function in Excel also requires you to combine cash flow 3 and horizon value 3 as well. With a non-constant growth stock, neither the dividend yield nor the capital gains yield are constant during the super growth period. As you can see here, the dividend yield, at time 0, the dividend yield is 5.6, capital gains yield 7.4, still adds up to 13. Though G and DY are not constant during the non-constant growth period, they still always have to add up to the required return. The third technique we'll look at to value stock is called the market multiples technique. It serves as something of a benchmark rather than a rigorous valuation method. Probably the most commonly used multiple is the PE ratio. Other entity multiples can be used. Be aware that using entity multiples values the entire firm, much like the free cash flow method, so debt and preferred claims must be subtracted. The trick is to find comparable firms, compute and average their entity multiples, and apply the result to your firm. Once the entity value is estimated, remember this is a value for the entire firm. Subtract debt and preferred as before and divide by the number of shares to get a share price. Market multiples is not a rigorous valuation method in itself. It is often very hard to find comparable firms. When comparables are found, their ratios may span a very wide range, which makes choosing a benchmark difficult. Clearly, the dividend growth model and the free cash flow model follow the same methodology. The free cash flow method has some advantages, however. It doesn't require that a firm pay dividends or that the dividends grow at a constant rate. It can also be used to value divisions as well as the whole firm. It only requires forecasted free cash flows. However, the free cash flow model, while providing insight into value drivers, does require more effort in the forecasting. Our last topic in Chapter 7, preferred stock. Preferred is a hybrid security with some of the characteristics of bonds, some of common stock. Preferred typically has a fixed dividend, which is paid in perpetuity. Preferred dividends must be paid before common stock dividends, but preferred dividends can be omitted without penalty. Usually, dividends on preferred stock are cumulative, meaning the firm must catch up any that were unpaid before any common dividends can be paid. Since preferred dividends are paid in perpetuity, the value of a preferred share of stock is simply the annual dividend divided by the required rate of return. As with common stock, we can observe the dividend in the current price. We need the required return on preferred for use in calculating the weighted average cost of capital. To find the required return on preferred, simply solve the equation for R sub PS, equation 722. This ends Chapter 7. In Chapter 8, we'll look at stock options.